Hello everyone and welcome back. In this video we are going to evaluate one of the most important aspects of a bolted connection, the clamping force and the safety against sliding according to VDI 2230. So we will use a real example that we have already modeled, and by the end of the video you will know whether these joints are capable of transmitting the applied load without slipping. So for this purpose, in the previous video, actually we already defined only an upward force of 20 kilonewton on the top of this face of this top plate. And in order to check the safety factor against sliding, so it was reasonable to have some forces on the shear direction. So I did in addition to the 20 kilonewton upward force, I did add a 5 kilonewton in the x direction. So the bolt would be a little bit loaded in the shear direction. So for this sake, we are gonna to check the safety factor against sliding, using analytical way. And for that, I already prepared for you an Excel file with this beautiful table, as you can see, with these all parameters that we are gonna to discuss in a bit together, step by step. So let's get started. First of all, the bolted joint consists of two round steel plates. Each plate has a thickness of 5 mm, and the plates are connected using 4 M8 bolts with a strength class of 8.8, and each bolt is pretensioned with a preload of 18.6 kN. So in the previous analysis, we already determined the load factor phi, which is tell us actually how the external load is shared between the bolt and the clamped part. So now we will use that information to evaluate the clamping force available in the joint and verify the resistance against sliding following the recommendation of VDI 2230. So before we started, actually many engineers think that the bolt mainly carry the external load in shear. But in reality, for a properly pretensioned joint, that's not the desired behavior. The preload creates a compressive force between the connected plate, and as long as the external shear load that we have, for example the 5 kilonewtons that we already defined, smaller than the friction force generated by this compression, the plate will not move relative to each other. So that means the bolts are protected from direct shear loading, improving fatigue life, and increasing the reliability of the connection. So in many bolted joint, friction and not the bolt shank is actually responsible for transmitting the load. What that means exactly in numbers, so we are gonna see that together in this table. So as you can see now, we have on this table many parameters to be input in order to get finally the safety factor against sliding. And first of all, for the used bolt in our model, we already took a bolted pretension of 18.6 kilonewton or 18,600 newton. We have 4 bolts in our model, and that's make in total actually an initial clamping force of 74,400 newton, which is the number of bolt multiplied by the bolt pretension. Now we already know that we have an upward force of 20 kilonewton, which is actually responsible to reduce the clamping force that we have on our plate. But it will not be completely substituted from this number. So the upward force that we have, the 20 kilonewton, with the load factor phi that we already calculated before, which is 0.182, and this factor is actually depending on the bolt stiffness and the clamped members parts here stiffness. If you want to check this, you can see the previous video. I already talked about it, so you can check it and know how to get it. And using the load factor phi and the upward force that we can have actually the external load taken by the bolt this is like first of all, so the bolt will take only 3640 Newton out of this 20 kilonewton. And here we are mean actually the all 4 bolt, not 1 bolt. And the remaining actually forces, which is the reduction in clamping force, will be actually 16,360 Newton. These forces will be actually substituted from our initial clamping force, which is like give us at the end like 58,040 Newton. So that what remain for us as a clamping force. Now, in this model, I already defined a frictional contact between these two plates with a frictional coefficient of 0.12. In your model, it could be like variable, so it could be like 0.1 or 0.15. It depends on the material used and the surface finish that you have. That of course can affect, like in some cases, like hugely the safety factor against sliding, because having like higher frictional coefficient that helps like to maintain the parts like together, like and against like sliding. In case it's like the frictional like too low, it's like in that case you need like a high bolt pretension or hold high pretensions like to maintain this plate together and avoid like sliding. So after knowing the frictional coefficient, we multiply this number by the remaining clamping force, and we will know actually the available friction force. So that's mean the maximum force that we could like handle before the top plate actually will begin to slide. And that force in our case is actually 6,964 Newton. As I already mentioned on the beginning of this video, I already defined a 5,000 Newton in the x direction, so we can like input this value there, apply shear load, so you can put for example 5,000 Newton there, and the available frictional force was like greater than our applied shear load, which is like give us like a safety factor against sliding of 1.39. So the interpretation actually is straightforward. So if the safety factor is greater than 1, sliding should not occur. If it's like close to 1, so the design has a little reserve and improvement it might be needed. If it's less than 1, that joint is expected to slip and the design should be improved for sure. Depending on the application, engineers often target a higher safety margin to account for uncertainties such as friction variation, manufacturing tolerances, and service conditions. So after substituting the calculated values for the remaining clamping force and the applied shear load, we obtain the safety factor against sliding for this bolted joint. So this result tells us whether the preload generated by the 4M8 bolts is sufficient to keep the plate locked together throughout operation. So actually, and VDI 2230 recommend for static problems like to have a safety factor like to maintain this like above 1.5 in some cases, and for dynamic scenario where your like parts like dynamically will be loaded, it will be like recommended to have a safety factor against sliding higher than 2. So in my case, and if I have like 5 kilonewton in the x direction as a shear load, it will be like recommended to have like same bolt size with a higher strength class, so we can have automatically like higher bolt pretension, or we can use like bigger like a bolt, like instead of the M8 bolt we can use the M10 bolt, so we can like ensure like having like higher safety factor against sliding. As we saw in the previous example, we already like have a very small like safety factor against yielding for the used bolt, and there is 20 kilonewton upward force. So based on these two like safety factors, now it will be recommended like to choose one of these options, like going with a bigger bolt size, or like choosing like higher strength class for the M8 bolts. Now, one important observation is that increasing the bolt preload generally increases the resistance against sliding because the friction force become larger. So if we have, for example, here higher bolt pretensions, automatically we will get higher force here, and comparing that with our applied shear load, we are expecting to have higher safety factor against sliding. However, preload can be increased indefinitely, so a higher preload also increases the tensile stress in the bolt and may approach the allowable proof load, which is in our case actually. So this is why selection the correct preload is always a balance between preventing joint separation, preventing sliding, and avoiding bolt overload. That balance is exactly what VDI 2230 helps engineers achieve through a systematic design procedure. So you have to maintain all safety factors above the recommended safeties, according to VDI 2230, to ensure a safe application. So if you are validation this joint using a finite element analysis, it's also important that the bolt pretension is modeled correctly. A realistic preload allows that software to predict the actual contact pressure between the clamped part, which is directly affect the frictional behavior and the calculated resistance against sliding. Without a proper pretension, the simulation may significantly underestimate or overestimate the performance of that joint. So now to summarize what we learned in this video. So we analyze a bolted joint consisting of two rounded steel plates 5 mm thick. We have 4M8 bolt with a strength class of 8.8 and the bolts are pretensioned with a 18.6 kN. Using the preload together with a previously calculated load factor phi, we evaluated the available clamping force and verified the safety against sliding according to VDI 2230. This is a critical verification because many bolted joints rely on friction to transfer shear loads rather than allowing the bolts themselves to carry that shear. So understanding that this concept is essential for designing safe, durable, and reliable mechanical joints. In the next video, we will investigate the difference between modeling a bolt as a beam element, as in our model right now, and as a solid model in ANSYS. So we will discuss how each approach affects the results when a solid bolt model is absolutely necessary and when a beam representation provides sufficient accuracy while saving significant computational time. So if you found this video helpful, don't forget to like the video and subscribe to the channel so you don't miss the upcoming engineering tutorials. Thanks for watching and I will see you in the next video.